Let's talk about how to solve systems graphically now. The graph of any equation is just the set of all ordered pairs that cause that equation to be true or correct. And if we sweep out every single set of points that causes an equation to be true, we'll end up with a line or a curve representing the graph. That means that when we're solving a system, if we graph both of these equations, then the point where the two functions intersect will end up being a valid solution to both equations, and therefore will be considered to have solved the system of equations. So let's look at this example where we're solving the system of equations 3x minus y equals 2 and x plus y equals 2. If we graph the first of these equations here, we can see that every single point on this line satisfies this system of equations. If we take 3 times the x coordinate minus 1 times the y coordinate, this will be 2, and you can check that for yourself if you want. If we also look at all the points that solve the equation x plus y equals 2, we can see that most of them are different except for the point 1, 1. If we look at this, 1, 1 indeed satisfies both of these equations, because 3 times 1 minus 1 equals 2, and 1 plus 1 equals 2. So we can say it satisfies both equations, or alternatively, it satisfies this system of equations. Let's take a look at why this doesn't always work, though. We're looking at a graph of the solutions to the equation 5x minus 3y equals 7, and the solutions to the equation 2x plus y equals 4. Once again, we can see that they intersect at only one point, giving us x equals 1.727 and y equals 0.545. So clearly, the solution's a little messier than before, but this should still work, right? Well, let's see what happens if we have the point 1.727 and 0.545. Let's take a look at what happens when we plug them in. 5 times 1.727 minus 3 times 0.545. If we plug this into a calculator, sure enough, that is exactly 7. We'll give that a check mark. However, if we look at 2 times 1.727 plus 0.545, double check me if you want, type this into a calculator, we get 3.999. What happened? Why isn't this 4? We verified that this worked graphically. The problem is, solving equations graphically doesn't give you exact answers. These solutions that we found are rounded and therefore don't actually solve this set of equations perfectly. They're off by just a little bit, and so they don't actually provide the exact correct solution that we're looking for. In class, we'll talk about how to deal with this, as well as why we need systems of equations, how to accurately solve systems of equations without graphing, and we'll go over some word problems that represent systems of equations. See you there.